So in this video, I'm going to discuss about stiffness matrix for bar element. Okay. So this is very common in the examination to make the derivation of the element stiffness matrix of finite element method. Okay. So this can be the formation by using the direct method. So now let me take a bar element. Okay, a straight bar element. So the loading arrangements like this. The one load for this, generally for a bar element the load will be applied at their ends, and the nodes are 1 and 2, and the cross section of the bar A and Young's modulus E or modulus of elasticity. L will be the total length of the element, and K is equal to K is the stiffness. Okay, so for a bar element K is equal to, it is AE by L. Now the force applied is F1 and F2 at node 2. So due to this loading condition of F1 and F2, some displacements that are produced at the node 1 and node 2. So at node 1 the displacement will be U1, and at node 2 the displacement will be U2. So due to their initial position. Since the displacements are produced at two nodes simultaneously, so the loads or the applied forces are equated with net resisting forces. Okay, for to make very clear understand here, I will draw one more figure. For example, with the same element and with the same loading condition, if we fix the one end, say here the loads are F1 and this is node 1, this will be node 2, and we made node 2 as 0. It means U2 is 0 because of it's a fixed end. Okay, because there is no displacement at 2. So you need to define the stiffness. So stiffness is what it is, a K is equal to force per unit displacement. Stiffness is equal to force per unit displacement. So you can write where F is equal to K into U in general. Okay, now the same equation we can relate it to the above this figure. Here we can say this for F1, F is equal to the force 1 and K, and displacement will be the here. Okay, at node 1 there will be displacement that will be along the force. Okay, in the same direction. Which one? The U1 will be applied, or it will deform along the force. So it means U1. Okay, so it will be taken as plus because it is in the same direction. For example, with the same diagram, if there is a displacement at 2, okay, there are some displacement that may be produced at node 2 which is in the opposite direction to the force of F1. Okay, so the displacement will be produced at 2 will be opposite to the U1. It means U2 will be opposite. It means having minus sign. Okay, so that F1 is equated to the resultant forces now, right? So same equation can be written as F is equal to F1 is equal to its K, and the displacement will be U1 minus U2. U1 minus U2 are the displacement, because where the U2 is applying or it is deforming in the opposite direction because of the resultant forces. Okay, now say this equation 1. So hope you understand why this minus sign, because it's in opposite direction. Similarly, we can make for the another condition. For example, with the same element, so node 1 and node 2, displacement will be same as u1 u2, and the direction of force is also same, this one and here this one. Now here we will make the node 1 as fixed, remember. Okay, so here it will be u2 and here it was u1. So now there is no consideration of f1, so because it's fixed, right? And displacement at 1 will be u1 and here u2. Now you can write for the displacement for f2. So same equation, like f2 is equal to k into u2, because the load along the load the displacement u2 will be produced. It means k u2. Now if you assume what u1 should be some values, like in the previous case u1 should be some values without having the fixed loads, and also to the opposite direction of f2. F2 opposite direction means in this direction, u1 having opposite direction of f2. Okay, now f2 is equal to k1, so it is u2 minus u1, u2 minus u1, because u1 is producing opposite to the f2. Okay, so in the same these two equations 1 and 2, if you arranged in the matrix format, equation format, so f1 is equal to k u1 minus u2, or you can write like f1 is equal to k u1 minus k u2. Okay, now second equation where f2 is equal to k u2 minus u1, you can write modified again, f2 is equal to k u2 minus k u1. Okay, now make this in the matrix equation or finite element equation. So this force vector as f1 f2 and matrix k minus k, again here this we have to again still modify, because k1 means u1 for first, make k u1 plus k u2. So first you have to write u1, second you have to write u2. So here you will get minus k and plus k, and outside this matrix u1 minus u1 u2 are the displacement vector. Okay, so here we can say this is as equal to f k u. It means k is equal to f by u. Okay, so this is the stiffness matrix formation or finite element equation. Okay, so here you should know the value of k that already I have mentioned in the starting. It is a by l, a by l. So if you take this equation again, I am modifying. If you make K outside, that is AE by L, and in the bracket you will get 1 minus 1 minus 1 1, and displacements are U1 U2 is equal to force vector F1 F2. So this is the finite element equation for a bar element, or stiffness equation for a bar element. Okay, so thank you for watching. Have a good day.